Hi everybody, I hope this video finds you well. In today's video, we're going to be finishing up section 10.3, which was our introduction to polar coordinates and also graphing in polar coordinates, which is going to be the main focus of this video. So what we're going to do in this video is look at a couple examples of graphing in polar coordinates. We're going to work through each of these examples sort of from a brute force perspective by building a table of values and then sketching a graph. And then at the end of each example, we'll talk about how the example we were doing sort of is indicative of a overall family or general type of curve in polar coordinates. And then we'll talk a little bit about those general types or those general families of curves. So in some ways, you can sort of think about this as similar to when you first learned graphing in like a basic algebra class and you learned certain classes of basic functions like parabolas, rationals, lines, etc. We're going to do something sort of similar here and just talk about some main types of polar curves. So to do this, let's go ahead and start with something pretty straightforward. We're going to try to consider the polar curve r equals 6 cosine theta. So here the radius is determined by this function of the angle theta. And we're going to graph this curve using a table of values. And after we build our table of values, we're going to make use of this, which is sometimes called a polar graph paper or a piece of polar paper, something along those lines. You guys can find your own copies of this posted in the file section of your Canvas course. So if you want to make use of polar paper, feel free to do so. It does make things easier than having to do by hand what I was doing in the previous video where I was drawing those concentric circles and then trying to locate the angle and everything. This makes things much easier because these pieces of polar paper already have these circles and you can choose sort of what spacing you want. So you could call that radius 1, 2, 3, or you could call that radius 2, radius 4, radius 6, whatever you like. And it also labels some main angles here. So let's go ahead and make a table of values over here. So we'll have our theta, and then we'll have our r equals 6 cosine theta. Generally speaking, a good sort of rule of thumb is that if you have a trigonometric function, which you often will when graphing in polar coordinates like this, you know that the period of this is 2 pi. And if you go by an eighth of the period, you should generally get a good amount of sort of points and things shouldn't be particularly difficult. So if we do that and we do 2 pi divided by 8, that would be pi over 4. So let's go by increments of pi over 4, which are nice and easy to plug in. So we'll have 0, pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, and 2 pi. So let's plug these values in. If we plug in 0, cosine of 0 is 1, so we get 6. If we plug in pi over 4, we get root 2 over 2. 6 times that is 3 root 2. If you have a calculator handy, it's not a bad idea just to get a sense of that number. It's pretty useful to remember that root 2 is about 1.4. So multiplying it by 3 gives us something about 4.2. So we'll just make a note there. That's about 4.2. For pi over 2, we will get 0. For 3 pi over 4, cosine will become negative, and we'll get negative 3 root 2, which will be roughly about negative 4.2. For pi, we'll get negative 6. For 5 pi over 4, we'll get negative 3 root 2, which is again going to be about negative 4.2. For 3 pi over 2, we'll get 0. For 7 pi over 4, we'll get 3 root 2, which will be roughly 4.2 there again. And then for 2 pi, we will get 6. So let's plot these and think about what sort of shape we're drawing here. So when we go to label this, I guess I'll go ahead and just label that as 1, 2, 3, 4, 5, and 6. So each circle is 1 unit of radius further. So my first point is 0, 6. So that means I'm looking at an angle of 0, so straight along the x-axis, and I go 6 units in that direction. So my first point should be right there. Then I'm at pi over 4, and I need to go to 4.2. If here's pi over 6, here's pi over 3, you can sort of see pi over 4 is right there, a 45-degree angle. And then 4.2 puts me a little past the fourth circle, so somewhere right about there. So it looks like I should be maybe right there. Again, we're just trying to get a decent approximation. And then pi over 2, which means we're looking straight up the y-axis, we have a radius of 0. Now, what does it mean to have a radius of 0? Well, whenever you have a radius of 0, which we have twice, that means you go back to the origin. Because it doesn't matter what angle you're facing, if you don't move, or you move with 0 units, you're back at the origin. So we know we should have something like that. Now, we could go ahead and get more points, but it's very useful when graphing in polar coordinates that whenever you return to the origin, you might want to draw in what you've seen so far. So if you think about it, what we should do is we should sort of draw this coming in, connecting here, and then swinging back in here. Now, a couple things. You'll notice that as I draw that, I always am making sure that as I draw that in, I'm inside that radius 6 circle, because certainly we're cosine, the biggest it can be is 1, so the biggest radius we can get is 6. So notice my curve is safely tucked inside of there. And you'll also know that I make it back into the origin before that pi over 2, because we know right at angle pi over 2 we get 0. So you shouldn't draw this thing looking something like that. That wouldn't make any sense, because we know it gets back to the origin by the time the angle is at pi over 2. So it looks like it should be something like that. So we'll try our best to sort of connect that there. Alrighty, something like that. There we go. All right, now we've done all these. Let's go ahead and start with 3 pi over 4. 3 pi over 4 would be looking this way, but we're going to back up 4.2 units. So instead, we're going to end up over here. So if we back up along that, we should end up somewhere right about here, it looks like, because if we sort of follow that line, yep, there we go. So now we're here, and then at pi, we're looking this way, but we back up 6 units and we end up there. Now, since that runs back into our curve, we might as well sort of draw that in. So I'll draw this thing in here, connect there, and then swing back in, and remember not to go outside that radius 6, and there we go. All right, so now we've done this. What about 5 pi over 4 negative root 3 over 2? Well, 5 pi over 4 puts us facing down this way, but we're going to back up 4.2 units. Notice that that's going to put us right here. So actually, as we go from pi to 5 pi over 4, we're actually retracing this section. Then 3 pi over 2, we hit 0, so that means that we swing back around through here. And then 7 pi over 4, we'd be facing this way down this angle here, and we'd go 4.2 units, which would mean we'd reach here. So that means that we go from here to here. So we're retracing our diagram. And then 2 pi and 6, 2 pi faces this way, 6 is out here. So we would retrace from here to here, and then from here to here. So actually what happens is, even though we went from 0 to 2 pi, which is the standard period of cosine, it actually caused us to trace out our graph once and then a second time. So we actually complete our graph twice, even though we did from 0 to 2 pi. All right, so there we go. There's our first graph in polar coordinates. What does that sort of graph look like? Well, it sort of seems to look like a circle. Now, is it a circle, an exact circle, or is it something that just sort of looks like a circle? Well, it turns out that this is exactly a circle. We can actually confirm that by taking a look at the equation. So this shape right here, and this turns out to, this is actually a circle. How is that? Well, let's take our equation, r equals 6 cosine theta that we just did, and let's try to remove the parameter. Now, to do that, remember we had that nice sort of relation that r squared was x squared plus y squared. And we also had a relation that r cosine theta was equal to x. So notice we could get those two things by multiplying both of these by r. So if we multiply both sides by r, we get 6r squared equals 6r cosine theta. We can replace this side with x squared plus y squared, and this r cosine theta with x, so we get 6x. Then notice you could rearrange that as x squared minus 6x plus y squared equals 0. We could do a little completing the square, and we could add 9 on both sides. So if we did that, x squared minus 6x plus 9 plus y squared equals 9. And that's x minus 3 squared plus y squared equals 3 squared. So this is a radius 3 circle centered at 3, 0. So let's see if that bears out with my diagram there. Centered at 3, 0. Yep, there's the center right there. And then that is radius 3. That's radius 3. That's radius 3. That's radius 3, right? It's 3 units out in all directions on this circle here. So what this graph actually is indeed a perfect circle here. So as our first example, let's just recap how we did this in terms of the thinking here. So when graphing in polar coordinates, the main thing to sort of remember is you should sort of treat this like a parametric curve. In polar coordinates, you're going to get a lot of smooth curves. It's very rare that you get sharp sort of pieces. So notice that the way we sort of did this is we got our first couple points. We were here, and then we were here, then we were here, and we came up with a smooth way of connecting them. We also made use of the fact that we knew we couldn't leave the radius 6 circle, and we also knew that we had to make it back into the origin before we hit that y-axis, right? It couldn't sort of loop out past, because then it would be an angle past pi over 2 that would have given us 0. We also found out that by the time we had hit pi negative 6, we actually had already finished the circle, and all of this stuff just repeated the same picture. This again goes back to that non-unique representations. Even though these were different sort of angles that we plugged in different radii than what we got up here, they were giving us the same points. So that's something that can happen with these polar curves. All right, did it just turn out that this one happened to be a circle? Well, it actually turns out that things of this form in general are circles. So let's talk about this as our first family of polar curves. So circles in polar coordinates. So it turns out that the equation r equals a sine theta or r equals a cosine theta, both of these create circles of radius a over 2, so whatever the coefficient in front is divided by 2. Notice that here it was 6, so we got a radius 6 divided by 2 or radius 3 circle. And if you have sine, then the center is going to be at 0, a over 2, so the center will be on the y-axis. If you use cosine, then the center will be at the x-axis, a over 2, 0. So just as two quick examples, we're not going to go through and graph these on our own, but if you want to, you can check that if we had r equals 3 cosine theta, we'd have a circle here that would have its center right there at 1.5 and be radius 1.5. And if we had r equals 4 sine theta, which is the blue curve, the center would be at 0, 2, and the radius would be 2 units in all directions. If we did something like negative 3 cosine theta, you'd have a circle just on the other side. If you had negative 4 sine theta, then the center would be down here, and you'd have a circle down there. So anytime you see a coefficient times cosine or sine of theta in polar coordinates, that's going to form a circle centered with its center either on the x or y axis. Okay, so that's the first family of polar curves that we wanted to know. Since we've talked about this now, if you see a exercise or a problem where you need to graph one of these, you still probably want to use some of a table of value, but when you do that table of value, you already know what sort of shape it should make. It's just how like when you graph a parabola, you know that it's going to make a parabolic shape. You only need to get a couple points, and it makes things much easier because you already know the shape that the curve should have. Same thing here now. If you see a sine theta or a cosine theta, you know it's going to be a circle. You even know its radius and its center, maybe get a couple quick values on a table of values, and you should be able to sketch it very quickly. All right, let's take a look at another example then. So we're now going to consider the polar curve 3 plus 2 sine theta. So notice if it was just sine 2 sine theta, then that would be a circle of radius 1 centered at 0, 1. But we have this 3 outside. So this is going to give us a different family of curves. So let's go ahead and make our table of values. So we are going to have our theta, and we're going to have r equals 3 plus 2 sine theta. Let's do the same sort of trick. Let's just do 0, pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, 2 pi. Remember, when making a table of values, you can choose anything you like, but you want to choose something that's relatively easy to plug in, and certainly plugging in multiples of pi over 4 into a trigonometric function is very straightforward. So if we plug in 0, we're going to get 3. When we plug in pi over 4, we're going to get 3 plus root 2. We said root 2 is about 1.4, so this should be roughly about 4.2. If we plug in 2, we should get 5. If we plug in 3 pi over 4, we're going to get 3 plus root 2, which is approximately 4.2 again. If we plug in pi, we'll be at 3. We plug in 5 pi over 4, we're going to get 3 minus root 2, which is going to be roughly 1.6. 3 pi over 2, we're going to get 3 minus 2, which is 1. 7 pi over 4, we're going to get 3 minus root 2, which is roughly 1.6. And 2 pi, we're going to get 3. Okay, let's go ahead then and plug these points onto our graph and take a look at what we're graphing here. So when the angle of 0, radius 3, that means we're facing this way and we need to go 3 units. Since we have a radius of up to 5, I guess we'll go ahead and still label 1, 2, 3, 4, and 5. So each circle just being a radius of 1. So our first point should be right there, right along the x-axis, 3 units along. Then we have 3 plus root 2. So following this angle here, we need to go to 4.2, which looks like we should be right sort of up here. There we go. Then at pi over 2, so facing directly up the y-axis, we have a radius of 5. So 1, 2, 3, 4, 5. Looks like we should be right there. Notice you can also use a little bit of common sense to realize that that's the maximum radius. So our entire graph should live inside of this circle here because the biggest sine can ever be is 1. 2 times 1 is 2, plus 3 is 5. The biggest our overall radius can be is 5 there. At 3 pi over 4, we get 4.2, which is meaning that we're getting something right about there. So we should have a point right there. Then at pi, we're facing this way, and we have a radius of 3. So it looks like we should be right there. Then at 5 pi over 4, so we're facing down this way. Notice we still have a positive radius, 1.6, so we'd still actually move into quadrant 3 there. So a radius of 1.6 should put us maybe somewhere right about there, sort of between the 1 and 2 radius. Then at 3 pi over 2, we're looking directly down this way, and we're at radius 1, so we should be right there. And then 7 pi over 4, we're going this way. 1.6 is the radius, so it looks like we should be right about there. And then 2 pi facing this way, 3, we're going to close up our curve. So let's go ahead and draw this thing in. So as we go from here to here, we're sort of having the radius get larger and larger and then larger and larger. There, now it's going to start getting smaller. Pull that back in, smaller, smaller, and then right here. And there we go. So we're making that sort of shape. So let's go ahead and draw that in. There we go. Little ugly there. Let's just go ahead and redo that. Okay. There we go. So there's our graph for 3 plus 2 sine theta. Now you'll notice that when I drew in here, I sort of made it go like flat for a moment and then smooth back out. Until we do 10.4 where we'll learn about how to calculate the derivative of polar functions, we don't quite know exactly what should happen here. You could reason out that this sort of makes sense. It doesn't really make sense to have a sharp corner there because sharp corners are, again, pretty rare in polar coordinates. But really, if you want to confirm why this thing sort of goes flat there and then smooths and then continues on, we'll have to actually wait until section 10.4 and know the calculus behind that before we can do it there. But there we go. There's our sort of function. Notice that it's no longer a standard circle because of the fact that this 2 sine theta sometimes is causing the radius to be larger than 3, sometimes causing the radius to be smaller than 3. So in this way, we go all the way out to radius 5, but this way, we're all the way in radius 1. So it sort of pushes in this section. You can sort of imagine this as a big circle where this section has been pushed in to sort of make that little indent there. Okay, let's take a look before we sort of summarize this type and see what happens if we reverse the positions of this 3 and 2. What would happen if we had 2 plus 3 sine theta? And it turns out something sort of very, very important happens there. So let's take a look. So we're going to quickly now take a look at 2 plus 3 sine theta, and we're going to see that while it's similar, it actually has a very unique feature here. So let's go ahead and take a look at this. So we'll have our theta, and our r equals 2 plus 3 sine theta. So same idea. Let's go ahead and get some values. 0, pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, and 2 pi. And let's plug those in. So at 0, our radius is going to be 2. Then we're going to get 2 plus 3 root 2 over 2. If we just type that into a calculator, root 2 over 2 is about 0.7, which we mentioned is a useful sort of value to sort of know. So if we take root 2 divided by 2, we get about 0.7 times 3 plus 2. This should come out as about 4.1. Then at pi over 2, we're going to have radius 5. Then 2 plus 3 root 2 over 2, which is about 4.1. Then at pi, we're going to have 2. Then at 5 pi over 4, we're going to have 2 minus 3 root 2 over 2, which is going to be 2 minus 3 times root 2 divided by 2. Just going to be barely negative, negative 0.1. At 3 pi over 2, we're going to get negative 1. Here, we're going to get 2 minus 3 root 2 over 2, which is, again, about negative 0.1. And at 2 pi, we're going to be at 2. So you'll notice something interesting happens here because we get negative radii. And remember, negative radii means we're actually going to be in the opposite quadrant. So let's go ahead and draw this out. So when we have 0 and 2, that means, again, if we sort of label here 1, 2, 3, 4, 5, we should start here. Then at pi over 4, going this way, we should be at 4.1, which puts us right up there. So should be something right about there. Then at pi over 2, we should be at 5. So we should be right there. Then at 3 pi over 4, we should be at 4.1. So if we follow this thing along, should be right about there. And then if we have pi, we have 2. Which puts us right here. Then at 5 pi over 4, we have negative 0.1. So we got to be very careful here. What this means is that we should be facing this way, but we're going to back up just a tiny bit and end up right over here. Then, really sort of important, 3 pi over 2, we should be facing this way, but since we're going to back up, we're going to be actually right there. So now we're going to have a point there. Then 7 pi over 4, we should have a negative 0.1. So 7 pi over 4, we should be facing down here into quadrant 4, but it will actually back up a little bit into quadrant 2. Notice also that since this is a continuous function, because we went from 2 to negative 0.1 and from negative 0.1 to 2, we must pass through 0. So there must be a couple moments where we go through the origin here. So let's go ahead and draw this out. Remember, we want to do this in order of the increasing sort of angle. So we're going to go from this point here. We're going to swing out to here. We're going to continue to swing out. There's going to be our top. Swing out, can still come through here. But then remember, before we hit that sort of middle line, we want to make it sort of back in here, to there, and to there. So it's going to have an inner loop here. So let's go ahead and draw that. So we said if we were going from here to there, to there, to there. Now we have to make it back into the origin before this line, since we know at that line we're already on the opposite side. So I'll try to scoot that thing in there. And then here. And there we go. So we have an inner loop there. So how do we know that it went like this rather than, sort of like that or something? Well, again, because you want to follow these angles. Remember, at pi, we were at 2. But at 5 pi over 4, we're at negative 0.1. 5 pi over 4 should put you into quadrant 3, but it means we're actually in quadrant 1 because of the negative radius. So we have to go from here to this point. So that means that that inner loop comes in under here, up, and around. So what caused this inner loop? Well, what caused this inner loop is the fact that now the coefficient in front of the sign was larger than this value. If you go back to what we had here, this value of 2 was not large enough for there ever to be negative radii. But here, because this was a 3, that 3 is larger than 2, there is the possibility for negative radii, which is what caused that inner loop there. So now we're ready to summarize this family of curves. And it turns out that there's several different types of pictures they can have based on the size of these two values. So let's go ahead and take a look. So the equations r equals a sine theta plus b and r equals a cosine theta plus b are what are called limosons. Limosons basically is just a French word for snail, because these things sort of sometimes look like a snail shell or a snail shape. These limosons have basically three cases. If that a, the coefficient of the sine or cosine in absolute value is greater than the absolute value of b, then they will have an inner loop. In other words, if this value here is magnitude larger than this, you will have an inner loop. You will have a sharp corner in the particular instance where a and b are equal, and we'll actually confirm that in our next video once we've learned the sort of calculus of polar curves, but we will see that if a equals b, they have a sharp corner. Sometimes this very special case where a equals b are called cardioids because, as we'll see in a moment, they sort of almost make a heart shape. Or they'll have a smooth piece, like our first example, if the absolute value of a is less than the absolute value of b. Generally, limosons that are based around a sine, so something a sine theta plus b, are oriented vertically, so they have vertical symmetry, whereas ones based on cosine of theta are oriented horizontally. So if you see a cosine theta plus b, it'll be sort of got horizontal symmetry. Here's three examples to explain what we sort of mean here. Here's 4 plus 3 cosine theta in red, 4 plus 4 cosine theta in blue, and 4 plus 5 cosine theta in green. You'll notice that each of these is horizontally symmetric, meaning that if you cut them sort of in half, the top and bottom are exactly the same. You will notice that for 4 plus 3 cosine theta, if you sort of zoom in here, you have that nice smooth bump. It sort of comes in here, hits that minimum radius, and then smooths back out. It's a smooth piece there. If you look at the blue curve, which is where you have 4 plus 4 cosine theta, well, right at theta equals pi, you'll get the minimum radius, which will actually be 0. So this thing comes swinging in. It actually makes a sharp sort of corner like that. And this is the one that we would call a cardioid because it sort of makes a heart shape. Finally, the green curve, which is 4 plus 5 cosine theta. Notice that this can make this negative once cosine is pretty negative. So especially at like cosine theta equals pi, you're going to get a radius of -1. So this guy is going to have that inner loop here. Right, here's all the components where it has positive radii, positive radii, positive radii. Here's where cosine equals -4/5, which causes it to actually have radius 0. Then there's the negative radii, negative radii, negative radii, back to another moment where cosine is -4/5, causing it to be 0, and then all positive radii like that. So what you can sort of imagine is that as this number here increases, you're sort of pushing this thing in, this little point here, further and further. Eventually it becomes sharp right when these two things are equal, and if you push it any further, what happens is that if you push this into there, it actually causes an inner loop. So you guys now know the general behavior of this entire family, the limoson family. So anytime you see something that's a sine theta plus b or a cosine theta plus b, you still maybe need to plot a few values, but you should already know the shape of it ahead of time. We'll also see some examples in our next section in 10.4 where we'll actually figure out exactly for things like this when that inner loop occurs. And of course, we'll be able to determine the angle where the sort of inner loop starts and then where it ends by looking at where the radius is 0. But we'll investigate that a little bit more in 10.4. We'll be interested in things like what's the area inside that inner loop or what's the arc length around that inner loop. For now, though, we've got one more family of sort of curves to look at. So we've got one more example to do here. So we're going to consider this our first polar curve that has a different argument than theta. All the other ones have always had an argument of theta. Now we're going to have an argument of 2 theta. And remember, that means that the period of this is cut in half. So to be careful with this, what we're going to do is we're actually going to, instead of going by like pi over 4, we might go by something like pi over 8, so that we can actually get more information since this thing's running twice as fast. So we still have our axes here. So let's make a table of values just like we've been doing. So there's our theta, and we have r equals 4 cosine 2 theta. We'll do some values like 0, pi over 8, pi over 4, 3 pi over 8, and then pi over 2. Now you might say, I'm not super comfortable plugging in pi over 8. Well, remember though, when you plug in pi over 8, it's going to be multiplied by 2, and the actual argument inside the trigonometric function is going to be pi over 4. So while we don't usually have like cosine of pi over 8 or cosine of 3 pi over 8 memorized, when we plug these in, we won't need to. Now we do have some more values. We'll have to do something like 5 pi over 8, then maybe 3 pi over 4, 7 pi over 8, and pi. Now, of course, we've got many more that we could do, but let's see if this gives us enough information to maybe intuit the rest of the graph here. All right, let's plug in 0. We're going to get 4. When we plug in pi over 8, we're going to get cosine of pi over 4, which is root 2 over 2. So this is going to be 2 root 2, which is going to be roughly about 2.8. When we plug in pi over 4, 2 times pi over 4 is pi over 2. Cosine of pi over 2 is 0. 3 pi over 8 is going to be 3 pi over 4. Cosine of 3 pi over 4 is negative root 2 over 2. So we're going to get negative root 2 over 2, which is approximately negative 2.8. When we plug in the pi over 2, 2 times pi over 2 is pi. Cosine of pi is negative 1, so we're going to get negative 4. 5 pi over 8, 2 times 5 pi over 8 is 5 pi over 4. Cosine of 5 pi over 4 is negative root 2 over 2. 4 times negative root 2 over 2 is negative 2 root 2. So again, about negative 2.8. 3 pi over 4 times 2 is 3 pi over 2. Cosine of 3 pi over 2 is 0. 7 pi over 8 times 2 is 7 pi over 4. Cosine of 7 pi over 4 is root 2 over 2. So we're going to get 2 root 2, which is about 2.8. And then when we plug in pi, 2 times pi is 2 pi. Cosine of 2 pi is 1, so we get 4. Now, of course, that's only going to tell us what happens from here to here, but maybe we can use symmetry to figure out what happens on the other part. So if we label, we can do 1, 2, 3, 4. If we want to, just for fun, let's give ourselves a little bit more accuracy. Let's actually label this as 1, this is 2, this is 3, and the very last one as 4. So I'm basically using each circle as half a radius unit, just so we can have a little bit more accuracy. And of course, I know the maximum radius is 4 because cosine can't be larger than negative 1 or positive 1. So my first point will be over here. Then I'll have 2.8. So 2.8 looks like there's 2.5. And so 2.8 maybe should be somewhere like in there. And then at pi over, that was pi over 8, excuse me, pi over 8. So pi over 8 should be here. If this is pi over 4, then this is halfway, so that's going to be pi over 8. So we said 2.8, so maybe right about there. And then by the time we are at pi over 4, we should be back at the origin. So let's maybe try to go ahead and draw that in. Now keep in mind, when we draw this in, we have to make sure that we make it back to the origin before that. So our curve would look something like that. So there's our first piece of our graph, and that handled this, this, and this. Now at 3 pi over 8, 3 pi over 8 should be up here. We have a negative radius, so instead of being in quadrant 1, we're actually going to back up down here, and we're going to go to 2.8. So that should put us right about there. Right? There's our 3 pi over 8, and we're backing up there. And there's half unit 1, 1.5, 2, 2.5. Yep, 2.8. There we go. And then at pi over 2, which should be facing this way, we're going to back up 4 units. So we're going to end up here. So we've got this part right here. Then at 5 pi over 8, which should be over here in quadrant 2, we again have a negative radius. So we're going to back up into quadrant 4. So it looks like we should be right about there. And then by the time we reach 3 pi over 4, which is here, or sort of here, we've got to actually swing through, connect, and before that line there, we have to close in. So you can see that this thing's going to swing down there, swing down there. Oop. And there we go. So we have this sort of closed leaf that swings around, gets in there before that that 3 pi over 4, 7 pi over 4 line. All right, I think we also had 7 pi over 8, which is down this way. Notice that that's in quadrant 2, and we do have a positive radius. So that's going to put us half a unit, 1, 1.5, 2, 2.5, somewhere over here. So maybe right about there. And then at pi, we're at 4. So we should be all the way out there. There we go. So remember, we started here, swung in through here, swung down here, swung through here, and now we should swing out to there. So there we go. All right. Now, is there more to do? Well, we could certainly add in more values like 9 pi over 8, or the next one I guess would be 5 pi over 4, 11 pi over 8, etc., etc. But you can probably reason out what's going to happen. We're going to swing around down here, come back in through here, then create one that goes up here, swings back around, and then at the end, we'll close this thing up. So on your own, you're welcome to try that if you want to. For now, we're just going to state that on sort of assumption. So we're going to have this thing sort of swing back through. Have this guy swing back through. We'll have that. Then we'll come on out here. This guy will swing up there. We'll swing down there. And then at the end, we'll come through down there. And there we'll go. And this thing will create this sort of 4-petaled graph if we went ahead and finished up all the way down to 2 pi. So there we go. This thing actually has these 4 distinct sections. And in general, when you sort of modify the period of one of these polar curves, you end up with this sort of petal graph here. Now, of course, the interesting thing is that we ended up with 4 petals, despite the fact that we only multiplied by 2 in the argument. It turns out that there is a general way to understand how many petals you're going to get based on whether or not the inside coefficient is even or odd. So let's go ahead and talk about that real quick for our summary of this 3rd family of polar curves here. So anytime you guys see things like a sine k theta or a cosine k theta, where that k inside is a positive integer greater than 1, so something like 2, 3, 4, 5, these are what are called petal graphs. If that k is even, so like 2 or 4 or 6, then the graph will have 2k petals, so it'll have twice as many as k petals. If that k is odd, then the graph will have exactly k petals. So here's 2 examples of that. The red curve is r equals 2 cosine 2 theta. So notice that since it's cosine 2 theta, there'll be 4 petals, in which case there are here. And 2 sine 3 theta, well, there's a 3 in there, so there'll be exactly 3 petals. You might say, what does that number outside do? Well, it just determines the length of those. Notice that whatever that number is the maximum radius. So the furthest out either of these will go is out to that radius 2 circle. They both live inside that radius 2 circle. You can think about how you would figure out the moment they achieve that. For example, like if you wanted to know exactly what angle this tip occurs at, well, it's not too hard to do that. That's where that radius is maximized, which is where sine is equal to 1. So you could think that you would have to basically solve sine 3 theta equals 1, which would mean 3 theta is pi over 2, which means theta is pi over 6. And if you look at our diagram, yep, that makes sense. At pi over 6, that's the sort of longest moment of that petal there. So this sort of brief go through in terms of polar graphing is supposed to show you guys several things, and I just want to summarize them really quickly. One is, if you're ever unsure about a polar graph, make a table of values. Remember that you're going to be plugging into a trigonometric function. So plug in angles that you know how to work with. Pi over 4, pi over 6, multiples of pi over 4, pi over 6, pi over 3, things like that. Make sure you plug in easy things so that you can make that table pretty easily. Second, remember that anytime you get a radius of 0, that means your curve returns to the origin. Make use of that. Third, as you're graphing in polar coordinates, always make sure to fill in portion by portion. You wouldn't want to do something like this, get all these points, then just draw them all on and then hope to do it. Instead, we have basically said every time we hit a 0, we sort of took the time to fill in that curve, then we filled in that piece, then we filled in this piece, and then we filled in that piece. So it was very easy to sort of trace it. And remember, that tracing had to be smooth. It doesn't go like here and then up to here. Now it swings through here, nice smooth motion, then through here, smooth motion, through, back through, and through. That's how we actually traced it out. So the reason we do these after parametric is because with parametric, you get a sense of sort of letting the parameter move forward. Same thing here, we're always letting that angle sort of sweep from 0 to 2 pi. Last thing is that in general, the polar curves that you will be asked to draw are going to come from one of these three families. So make sure you're comfortable with the family of sort of circles that we discussed here, a sine theta, a cosine theta. The family of limosons here, which are a sine theta plus b, a cosine theta plus b. Remember, they have an inner loop if this condition is met, a sharp corner if this condition is met, or sort of a smooth piece if this condition is met. And then finally, last sort of grouping, these petal graphs, where that k value in there determines the amount of petals. So that pretty much wraps up our introduction to graphing in polar coordinates. In our next video, we'll be moving into our very last section, which is 10.4, which quickly runs through how to do calculus operations like the derivative, area, and arc length on polar curves.